Thermodynamics of open biological systems. When we speak about variety of thermodynamic system, we should distinguish isolated, closed, and open systems. So, what we have? In isolated system, there is no exchange of energy or matter with environment, as we can see in this scheme. Closed system exchanges energy with the environment. So here we have energy exchange, but we have no exchange of matter. Open system are systems that exchange matter, energy, and information, which is inherent for living organism, with the external environment. So here we have, in this last case, we have all types of exchange with environment. Then, stationary system, we call the system which parameters do not change with time when interacting with the environment. And example of such stationary system can be human. The state of any thermodynamic system is characterized by physical quantities, which are called parameters, such as volume, pressure, temperature, density, etc. Thermodynamics parameter can be internal and external. Intensive and extensive, and so on. Thermodynamic or thermal equilibrium of the system we call the state in which parameters of the system do not change with time. The system can be in thermodynamic equilibrium for a very long time. As for main notions for thermodynamic, we have at least three such notions: internal energy, work, and amount of heat. Internal energy, which we denoted by letter U, represent the sum of potential energy of interaction of atoms or molecules of matter and kinetic energy of their motion. Energy at all is the ability of system to perform some work. So as it is obvious from such consideration, we have two forms of energy transfer: work and heat. Methods of heat transfer, we can speak about thermal conductivity, convection, and radiation. So the thermal conductivity represents transfer of energy between objects in their direct contact. Convection represents the process of transferring the energy by liquid or gas streams. To be exact, we have mixing of layers of gas and stream, and so we have exchange of energy between these layers. Radiation represents the processes of transmitting energy by the electromagnetic waves of different frequencies. The central role in thermodynamics play so-called the first and the second law of thermodynamics. So, as for the first law of thermodynamics, let us consider the interaction of closed system with environment. Energy exchange can occur due to the work performed or due to heat transfer. So let us look at the picture. Suppose there is a vessel with movable piston with cross-sectional area S that can move. The substance was placed under this piston and some heat was provided to this system. In fact, we can consider here gas or liquid or something else. As the gas temperature increases, the kinetic and potential energy of interaction of gas atom rises, that is, the internal energy changes. As a result, the pressure increases and our gas performs the work of lifting the piston, and this mechanical work, we can define as product P dV, where P is pressure, dV a small change in volume. And if we consider such cylinder vessel, we can find our change of volume as product of cross-sectional area and a small element of length which was traveled by movable piston. So the amount of heat that was provided to our system when to change the internal energy and the work performed by the system. So we can write this amount of heat as change of internal energy and elementary work. Internal energy here is function of state of our system. So we write here the full differential. Elementary heat and elementary work represent the function of processes. So we denote their changes as a small delta. To be exact, the sign of our performed work depends on our system do this work or the work is performed on our system. So the first law of thermodynamics, or the first principle, says that heat input to the system is expended on the change of internal energy and the work performed by the system on external objects. We should remember that the first law of thermodynamics is the law of conservation of energy, which does not show the possible direction of the process. When we consider the first law of thermodynamics and history of its discovery, we should mention that this discovery was made not only by physicists, to be exact, Joule and Helmholtz, but also by physician Robert Mayer. The verification of this law was carried out on calorimeters, in which the heat released by the body during the metabolic processes, evaporation, and with the extraction products was measured. And it was found that the heat released by the body fully corresponds to the absorbed energy along with nutrients. So from the first law of thermodynamics, it follows that the human body is not an independent source of energy. Then, when we speak about the second law of thermodynamics, it can be presented in the forms of more than 2,000 of formulation, and some of them you can see in this slide. For example, formulation of Clausius, 1865. In a isolated system, the transfer of heat from a less heated body to a more heated one is impossible. Another formulation by Thomson. The process is impossible if the only result of heat is heat to work conversion as a result of cooling the body. The second law of thermodynamics provides the direction of processes occurring in the system, and so on. So when we speak about the second law of thermodynamics, we come to difference in various thermodynamical processes. So reversible processes represent processes in which parameters which characterize the state of the system pass the sum series of numerical values, but in reverse order. So when we represent the state of system as point in such PV diagram, what we have? Our initial state denoted by 1 and our final state denoted by 2, and each point of this curve represents a certain state of system. So reversible processes say us that we can make this path in reverse order, passing through each of these states. When we speak about impossibility to pass this path in reverse order, we can return to our initial state only by another way. We faces the irreversible processes. Here is as well such type of processes as cycle or circular processes, which is process where the system returns to its initial stage. So we have such closed curve entirely, but the way towards and in reverse order is different. Then the second law of thermodynamics give us notion of entropy as function of state of system. To be exact, entropy was introduced as some sort of integration factor to the amount of heat. So for reversible processes, entropy can be represented as difference of two values of the system state function. So we have such definition of our entropy in final and initial state. It is integral of ratio of elementary heat of our processes divided by temperature. And correspondingly, S1 and S2 represent entropy of the final and initial state. In general case, our change of entropy can be presented in the form of inequality. So our change of entropy is greater or equal to this integral. So the sign equal corresponds to reversible processes and the sign greater to irreversible processes. According to this definition, the units of measurement of our entropy is Joule divided by Kelvin. We can conclude that reversible processes always occur in the direction of increasing of entropy. If process which we consider take place in isolated systems, so we have no exchange of heat, our elementary heat equal to 0, so the entropy does not change, our S2 minus S1 equal to 0, S remains constant. The entropy of isolated system increases as it approaches equilibrium, so in equilibrium state, entropy reaches its maximum value. So the processes which lead to decrease in the entropy of the system cannot occur in isolated system, and it gives us the second law of thermodynamics and possible direction of occurring of our physical processes. Entropy by its physical meaning characterize the degree of order or disorder of the system. According to the Boltzmann principle, entropy can be determined by formula S equal to K logarithm of W. Here is K is Boltzmann constant 1.39 10 to minus 23 degree Joule mole Kelvin, and W represent the thermodynamic probability or statistical weight, which give us simply the number of microstate by which just this empirical state of our system can be realized at given energy, volume, and number of particles. As for non-equilibrium thermodynamical processes in open system, Of course, real processes and states of system are non-equilibrium, and many systems around us are open. The total change in entropy in an open system can be represented as sum of two terms, DSI and DSE, whereas DSI is change in entropy inside our system, and DSE is change in entropy caused by the interaction of open system with the surroundings. Inside the real system, there are irreversible dissipative processes, as a result of which entropy can be accumulated. So the change of our internal entropy, DSI, should be greater than zero, should be positive. But there is no restriction imposed on change of entropy of environment, DSE. So this entropy can be either positive or negative. Stationary state, we call to the state of system in which the entropy of the entire open system S is conserved. So the total change in energy is zero, our ds whole equal to zero. So our internal change of energy and our exchange of entropy with external surroundings should be the same in value but opposite in sign. As we have positive DSI, then we obtain such equality. The entropy generated inside the system is completely transferred to the environment. Here we come to so-called Prigozhin theorem, which says that in the stationary state, the entropy production is minimal. This theorem enables to determine the direction of development or evolution of an open system of any degree of complexity. That is, if in our open system, irreversible processes take place near thermodynamic equilibrium, then by reducing the entropy production in such system, we make it possible to predict the transition of the system to equilibrium state. The system, due to internal irreversible processes, cannot get out of a stationary state. Prigozhin theorem also can explain the fundamental stability of stationary states of open system. If the open system independently leaves its stationary state due to a rise in fluctuation, then here we have an increase in the rate of entropy production. According to Prigozhin theorem, the necessary consequences of such a change in the state of the system should be such processes inside the system during which our system returns to its initial stationary states, and this give us the understanding of this give us so-called Le Chatelier-Brown principles, which explains the stability of the equilibrium system and says that any external influence that bring the system out of equilibrium causes in it such processes that tend to weaken the result of these external influences. Let us consider an example from open biological systems. So when we consider the photosynthesis, the inflow of free energy of the light give us appearance of complex glucose molecule and decrease in cell entropy. So our exchange entropy DSE is negative. And we obtain the decomposition of glucose during respiration in the cells, and this decomposition increase our internal entropy DSI greater than zero. Depending on the ratio of these rates of change of entropy DSI and DSE, the total entropy DS of our open system can either increase or decrease over time. So if we write the differential of expression gs equal gsi plus dse, over the time we obtain such rates of change of our entropy, or that is the thing, the entropy production. What we have, if our GSE prodigy is negative, and by absolute value GSE prodigy is greater than GSI prodigy, then the total entropy of open system decreases. And here we have GS prodigy negative. A negative value of production of entropy, or that is the same, the inflow of negative entropy corresponds to the outflow of positive entropy into surroundings, and the inflow of useful substances from the environment. Then, if by absolute value our GSE prodigy is less than GSI prodigy, then our entropy production is positive, and this corresponds to the general degradation and disintegration of open system. In the stationary state in open system, the next condition is fulfilled. Total production of entropy equal to 0. So here we have a rate of GSE prodigy negative, by absolute value GSE prodigy equal to GSI prodigy, so our production of entropy is 0. Very important when considering the thermodynamics of open thermodynamical processes is thermodynamic potential. We can say that any thermodynamic state of any system can be completely determined by thermodynamic potential. For each entire set of independent thermodynamical parameters, we have certain thermodynamic potential by which any macroscopic characteristic of system can be calculated. For example, the first known thermodynamic potential is obviously internal energy U for open one-component system. From the first law of thermodynamics, we can write that differential of internal energy U equal to TdS minus P dV. Or if we consider open multi-component system with a particle exchange, we have additional term in this expression. But when we consider various processes, sometimes it is very inconvenient to deal with parameters which is not observable, such, for example, as entropy. Due to Legendre transformation, we can change our independent parameters for energy potential to more convenient. For example, if we take our and internal energy and add it to it the product of pressure and volume, we obtain the enthalpy potential, or its second name is heat content. For full differential of enthalpy, we get such expression. And physical meaning of enthalpy we can get from the gas law. The thermal effect of chemical reaction does not depend on the part path, but it is determined only by the difference between the enthalpies of the final and initial substances. So our heat content of any chemical reaction represent the change in enthalpy. The change in the enthalpy or heat content of the system corresponds to the value of absorbed or generated heat. Then the next thermodynamic potential is Gibbs free energy. This potential we use in isobaric isothermal processes, so we can define it as the difference of enthalpy and binding energy, Ts, or as sum of internal energy, product of pressure and volume, minus binding energy, Ts. So as we take the energy and take from it the binding energy, we obtain free energy. We can write the full differential for Gibbs energy, and when we try to describe the behavioral system in isobaric isothermal processes, when our change of temperature or change of pressure is 0, we obtain the change in Gibbs energy is negative. And decrease in Gibbs energy takes place until the state of equilibrium is reached. So we obtain the possible direction in our real experiment. Then the next thermodynamic potential we call the Helmholtz free energy, defined as difference of internal energy and binding energy, or difference of enthalpy, product pressure and volume, and binding energy. In the differential form, we can represent the full differential of Helmholtz energy as minus S dt minus P dV plus mu dm. It should also be noted that under our usual condition, it is much easier to fulfill the requirement of constant temperature than the entropy, because our temperature is measurable and observable value. Therefore, the last two mentioned thermodynamic potential, the Gibbs free energy G and the Helmholtz free energy F, are more widely used to describe medical and biological system, because when we speak about biological system, for them isothermal isobaric or isothermal isobaric condition are most natural. The numerical value and the sign of change in the thermodynamic potential can determine the direction of processes. If as a result of process there is a decrease in thermodynamic potential, so if our dF negative or dG negative, such a process is spontaneous and occurs with the release of heat. If as a result of the process there is an increase in thermodynamic potential, our dF positive or dG positive, such processes is not spontaneous and occurs with the absorption of additional energy from surroundings. When we speak about negative change in the thermodynamic potential, we know that processes can be occurring in natural way. When our change in energy is positive, we know that we have external inflow of energy to make this process possible. As we approach the equilibrium position, the Gibbs free energy and Helmholtz free energy get their minimum value. So in equilibrium, we have minimum of our thermodynamic potential. When we speak about thermodynamic potential for multi-component system, in all our potentials, we have such additional term mu dn. So we can define the chemical potential as Gibbs free energy per mole of substance and constant temperature and pressure. So our chemical potential, which is energy required for exchange by one particle with surrounding, we can describe as derivative of Gibbs or Gern-Gold's free energy by amount of substance or concentration. The chemical potential usually has the form, whereas mu0 represents chemical potential of pure component, and here we have a concentration temperature term. C represents the concentration of our dissolved solids or certain ions. R is universal gas constant and equal to 8.31 joule mole Kelvin, and T is absolute temperature of our environment. For example, when we speak about electrolyte solution, which represent the most of our internal liquids in our organism, then in the presence of external electric field and taking into account the solute, the chemical potential we can present in the following form. Our usual two terms mu0 and RT logarithm T plus that phi phi. This additional term represents actually the work of electric forces is for moving the charge from one point to another. Here is Faraday number F equal to 96,485.34 coulomb per mole, which is electric charge of 1 mole of substance. Phi represent the electric field potential. C give us smaller concentration of solute, and that represent charge of dissolved ions in units of elementary charge. The driving force of chemical processes is the potential difference between the initial and final products, and we can say that if the potential difference is zero, then the process ends up and the system enters a state of equilibrium. So we obtain the criteria for our processes occurring in a biological system. So for today, it is all. Thank you for your attention.